All right. Here we go. Technology is recording, at least on my end. Welcome back. It's good to see large number of you today. I mentioned before I started recording that you know it's we need to move on to the next topic, and this is the sort of unified shader architectures topic. We're almost out of time in the semester, so we really just have a few more days together as a class. Um, and I don't think I'd be doing my job if we didn't at least start to cover this kind of topic. And there's certainly versions, like I mentioned, there's versions of this type of course where the entirety of the course is on just rendering, and maybe looking at more advanced rendering. And then there would certainly also, and there are many other versions of this course that are just doing CUDA programming, and so you can certainly build. And there are on campus, 15-week kind of CUDA programming courses. I think, at least in my experience, that there's a lot to learn there, and there's a lot of fun things to discover. Architecturally, this topic I think comes very naturally after we've covered what we've already covered, looking at vertex shaders and the like. Seeing kind of the evolution of the architecture also directs our evolution of our understanding of what's happening architecturally here. And I also think from a programmer's perspective, um, those of you who are juniors, seniors, graduate students, and all that in this general area, this computer engineering broadly speaking area, you're not going to find anything here that you can't handle. I don't think we need to spend a full semester on this topic, and we're not, right? And even if you do wind up taking those, HPC courses that do spend a good chunk of a semester on that, there are some other things you'll be learning. The tooling and the infrastructure itself is a major topic for those kind of courses. The actual programming and the syntax, it's new, it's different, it's nothing I don't think you can handle. So we'll learn the new things. You'll get a chance to explore on your own, and I think you'll be able to handle it without too much difficulty here. So I've split it kind of into two, although they kind of merge together. So today, a little bit more about the architectural side of things as an introduction, and then we'll get into more of the programming challenges associated with it. But the two topics are directly intertwined, just as they are for rendering as well. So the architecture influences how we do the programming, and the programming also influences evolutions in the architecture, and that is just as true for this as it is for conventional graphics rendering and processing. So briefly, very briefly, review of where we are and how we got to this point. We've built our own programmable shaders, literally two of them, right? We've built a programmable vertex and a fragment shader, and that is a reflection of state of the art of the early 2000s, 2003 time frame, where there was addition of these separate programmable processors, one for doing vertex shading, the kind of transformations we covered, and another for doing fragment shading, things like texture mapping and the like, amongst other programmable things that you could do there. Originally, they were two different ISAs, and we've talked about that a little bit. In our lab, there didn't seem to be a point. You could argue that maybe we don't really need to do texture mapping at all in the vertex shader, so we could remove that. But from managing the code complexity, it's probably easier for it to be a uniform shader for us than the other way around. Um, but in those early days, those were two different programmable processors with different ISAs, and they were physically in the pipeline, and they had a lot of restrictions, certainly in the early days of programmable of that. So very basic, if any, sort of branching type of statements. No sort of global view of memory. So the real main memory you had access to, beyond just the attributes of your vertices and fragments as they were coming in, would be from texture memory. And this led to, in those earlier days, this concept called general purpose computing on graphics processing units, a term that we still see used, but I think has been mostly relegated to this idea of you can use these graphics processors, and we're talking that 2004 era GeForce 6 series architecture, and I actually have it on the next slide here, that you could use these processors which were not designed to do general purpose computation and also have them do general purpose computation. So when you see that term, it's sometimes still in use for things that we refer to as more general GPU computing today. Um, it's a valid term, but I think it's for the most part being relegated to discuss this era of history, which is you have an architecture that looks like this. not so different from your simple graphics processors, right? Um, we could build ours is much narrower version of this, but it's doing very similar things, right? What we have built. Host processor assembles vertices, do some vertex processing. So each of these would be separate vertex processors of the types we talked about a few weeks back. Some initial triangle setup and rasterization, right? Generating our fragments, feeding that then to the next level of programmable fragment processing. Lots of data getting generated from that. We have a number of these, what we call, and it's still the right term for this, kind of render output modules there. So Z compare and blend. Well, that was MP4, right? So uh, our version of this is a lot more narrow because we just have one of all of those blue components shaded here. But for the most part, that has is what we've implemented. So when we refer to this term as GPGPU, and it's a bit of a mouthful, it's generally still referring to doing general purpose computation on these type of architectures. Um, and it was possible. Now there was limitations, right? So as I mentioned, originally at least, the vertex shader and the fragment shader were different ISAs. So that's already kind of a headache in and of itself, right? So and also at the time you're writing mostly assembly style code in those days, so you had to be very careful in terms of the code that you were writing for them. Also, although this picture doesn't really do it justice and show it appropriately, generally there was a pretty large imbalance between how many vertex processors you would have and how many fragment processors you would have. We probably, if we could reallocate resources in our design, would probably wanted to make a similar design decision. Group two, if they do a great job and we port to the new board, that'll be next year's class's challenge to overcome. We've already seen that, right? For three vertices, you can have a whole bunch of fragments. So it makes sense to dedicate more chip resources to doing fragment processing than vertex processing, even if the math that the code we want for each is roughly the same. So that was kind of a limitation there, but generally there'd be more of the fragment processors. And then finally, certainly in the early days, although that has changed, in the early days, you were really limited in that only the fragment processors could do the texture mapping operations themselves. Could actually read these big blocks of data from memory. So for that reason, in those early GPU days, it wasn't really using the whole chip for computation. It was really just using the fragment processing side of the chip for computation. And what that would mean in practice is that you would take advantage of the fact that you could in theory generate a large number of this says pixel, but it really should say fragments here. You would generate one thread associated with each fragment that would get created. So okay, pixel fragment, but we know the distinction here. So if you had a computation that you wanted to map to, let's say, 1,000,000 different threads, what you would actually do, and again, you can think of this as a hack essentially more than anything else, right? You would essentially just generate a large quad or a very large triangle. Um, that would correspond to 1,000,000 fragments in your render buffer. And then, in having done so and having this as our backing architecture, you would then have 1,000,000 different, if you want to call them threads, I think it's a valid thing to describe it as, but 1,000,000 different pieces of work for your fragment processors to take care of. Just like we do now, right? Even for our pass through fragment buffers, we could very easily, right now, with our lab infrastructure, generate we're not really thinking of them as threads, but they are, right? I mean, right? Every time we have a new fragment comes in for our MP4 fragment processor, we are running a program for it, right? So that is a thread of computation. So in this old school kind of sort of hackish way of doing things, if you wanted 1,000,000 threads of computation, if you had a piece of work that you could parallelize across 1,000,000 different threads of computation, you would first actually render a sufficiently large triangle, or usually a quad, but a sufficiently large geometric object to generate that exact number of threads. And then in terms of the data that those threads would be actually operating on, that all had to be formatted as textures. Today, that's no big sweat, right? Because today you can certainly have just floating point textures, and this connection between what is a texture versus what is just an array of memory is completely gone. But you can still see the vestiges of that when you look at some of the OpenGL documentation. That when we generate a texture, we didn't talk about all the API calls for this. I kind of realized that since we weren't implementing very much of that, I didn't want to cover too much more of the texture mapping topic. But there's a lot of those parameters where we very carefully dictate what the format is of our particular texture map. RGB generally, how many bits per component, and all the kind of weird legacy modes that we would need to have either images stored as or just for our individual data that we're representing images for our texture mapping. So that's the second reason it's a hack. So the first reason up there is yes, if we want a million threads, um, we need to generate a shape that's going to guarantee us a million fragments. Secondly, we know to do computation, we need some sort of data. All of our data in this GPU mode of computation was going to be formatted as a texture. So you'd be generating a texture map and it based on some file or some other way of generating the data, in which you're basically fooling OpenGL into saying, here's my texture that I'm doing a texture map for. Our text fetch type instruction or just the texture call in what's now GLSL. Um, but it wasn't actually meant to correspond to anything visual. It wouldn't look like anything, right? Real data doesn't look necessarily like anything when mapped as a 2D array. But we'd have to kind of, squish it into these RGB components of different size. And then finally, also our output would also have to correspond to one of our buffers, either our color buffer or one of our depth buffers. And that to actually get the results of our computation, the CPU would then read the results from those buffers. So historically, this is kind of an interesting, circumstance that happened. Is that I think it's correct to refer to this as um, a hack, right? To take this architecture and say, well, this was never intended ideally to do just general purpose computation. Let's trick data as texture. Let's trick threads as just generating arbitrary fragments that we don't actually care about the visual result of it, but let's render to a buffer, fool the GPU into think it's actually drawing something meaningful. We don't need to anthropomorphize it, but let it pretend that it's doing some sort of computation with regards to a graphical output, and actually just do a readout of that buffer at the end, and that's how we get our computation. But what happened is, of course, these GPUs, as generally just being used for their primary purpose, which is accelerating graphical rendering, was hitting that same kind of stride of all technology in that era, which was increased sort of exponential growth of transistor density, the ability to just put more and more and more of these in a given chip from year to year to year, and realization, and it wasn't sort of an accidental discovery, but the realization that in terms of just computational density, these chips, even though they weren't meant for computation, were extremely competitive. Things have evened out a bit more now outside of the margins, but at the time, it was kind of an astounding thing in terms of we have this chip that's meant to just fill triangles very efficiently and determine the color of fragments that are going to ultimately correspond to pixels on a screen, and the kind of math that those things are optimized to do, and the amount of parallelism that is sort of freely available based on the graphics rendering algorithm and the parallelism inherent in that, leads to a chip that, even though you have to kind of do some hackish things to get it to work, was extremely competitive in terms of floating point performance or just computational performance in general. And in that era, and maybe a few years after this initial release, and we're talking orders of magnitude improvement, that the amount of computational density on these chips were so much more than what was available in the CPUs at the time. So I don't think any of this was an accident. Um, and there was some very people with good foresight to realize that this is a potential future path. But that evolution was in part driven by the fact that these devices from around this era on could be recognized as being able to sort of serve both purposes. And very soon after that, you would have it's the same exact chip and the same exact hardware, but two different views of the hardware. One for sort of the graphics view of what could be rendered on this chip, and the other from what could just be done with general purpose computation on this chip in a way that became sort of directly supported by the manufacturers, by the runtime libraries, by the software languages as well. So more recently is that evolution of sort of unified shader architecture. So the realization that the task needed for vertex shading is really not all that different than for fragment shading and having a same ISA. So when we refer to unified shader architectures, at its base, all that means is one ISA. That we have one set of cores, this pool of cores to choose from, and there's a more explicit task and thread management associated with the execution in our GPU. That's all that unified cores or unified shader architecture means. What we built in our SGPs is essentially a unified shader architecture. I acknowledge that it is an exceptionally limited version of the possibilities that are out there, given our exceptionally limited budget and time allowance and things like that. But that's all that means. That the ISA is the same. Vertex and fragment shading, the math required by each, the expressiveness we needed in the language to program each, were so much of an overlap that it seemed worthwhile to have a general pool of these cores and to do much more thread management versus this previous architecture in which the thread management was much more statically allocated. In this case, if we happen to have an application that had a whole ton of vertices relative to its fragments, it's possible, then this design, which makes a static decision of resources, um, would be inefficient for that. Right? This is a design time allocation of how many cores are going to be doing vertex shading versus how many cores are going to be doing fragment processing. That has made it design time. The chip itself has that physical layout of n number of vertex cores versus m number of fragment cores. And they had different ISAs, but they really weren't all that different, but they did have different ISAs. This evolution of so-called unified shader architecture is a realization that there's enough similarity here. Yes, we still need to do some rasterization. There still needs to be some fixed function hardware for render output and for rasterization, but the rest of it can be entirely shared. And we just have to then be a little bit more clever than what our SGP architecture has for us in terms of how we do actual allocation of threads and mapping them to individual cores. Here, it's still very much a fixed function mapping. Vertices come in, we assign them, we rasterize, we assign then those fragments to fragment processors. If these set of cores are all part of the same pool of these set of cores, well, there's some benefits. We can handle different workload imbalance between number of vertex versus number of fragment tasks we have. We just have to be a little bit more careful in terms of who is distributing the work, what programs are they running, what instructions are they running when that work actually then does get distributed. But that's the unified shader architecture. And in doing so, it became a much more straightforward thing to then add an interface for more general purpose computation, this whole GPU computing. It is related but somewhat independent of that change to unified shader architecture. They coincided. So, which came first, which one drove the other decision is it's hard to say, and we don't really necessarily know which one came first. But the idea was that since we have these unified cores, in which it's now this large pool of resources that all share the same ISA for computation, we can then change our programming model for it. They didn't have to. They could have used unified shader architecture or designed unified shader architectures that didn't have a new interface for general purpose computation. But both things coincided. That we have this pool of cores that all share the same ISA, let us also then provide a more easy and more straightforward way to design applications to make use of the computational resources for that. So when we refer to this term of GPU computing versus GPGPU, so again, the slight caveat that some people still do use them interchangeably. You will find references all over the place that use the two terms interchangeably. I think at least it's nice to kind of separate the two. GPGPU, when you think of that, think of everything as a texture, every application is a fragment shader, and I'm kind of tricking the GPU into doing computation for me. That's the GPGPU. And I hope I don't have to use that again because I'm going to mess up the acronym. GPU computing is this unified shader architecture. We now welcome you to do computation on these on these devices. And here is programming languages, runtime environments. You can think of it as APIs and SDKs to do computing on these devices. So we no longer have to trick things into becoming textures for us. It's using the same exact hardware. And in fact, the changes between the generation of split vertex fragment shaders versus the first generation of unified shader architectures, it's a very subtle difference. We'll have to kind of squint to see the actual difference here. But it allowed just enough hooks so that we don't have to format our computation to map that general fixed function rendering pipeline. Things have grown and continue to grow at a really interesting rate. I actually just looked this up, over the weekend in terms of if not the most expensive, I think the most impressive GPU you can buy. Nvidia names their different generations of technology after scientists. There's the Ampere class hardware, which I do not have any access to yet. If the class is looking to put together, donations, for future research and things like that, this would be a nice relative bargain, I think, at just 4,600 for a single GPU here. But at least according to the documentation for it, this is a little mind-boggling to me, but it's over 10,000 streaming processors per GPU. Um, how the designers happen to manage all that complexity, the testing of that, I can't even imagine. Right? Think of the challenges we have for testing our two cores. Not all the challenges grow linearly with that complexity, but a lot of them actually do. How do you even simulate such a chip like that? Um, may not be as many lines of code, but just the number of transistors that must correspond to is a little mind-boggling to me. But for the most part, and oftentimes we have to kind of read between the lines of marketing and marketing driven documentation, and then what is truly the difference from one generation to the next. There are some interesting things that have been evolving since this change to unified shader architectures and CUDA becoming kind of the entry point for doing GPU computing. There have been. Some of those things are what gets covered when you take the class on machine learning architectures, which will be offered next fall, in which it doesn't do a lot of CUDA. I don't believe in that class, but covers some of the architectural things with tensor cores and things like that. There are some interesting things that have been changed. For the most part, though, and looking at each year's release and the marketing and then the actual documentation associated with it, for the most part, the difference between this $4,600 card, can't imagine what power supply it requires, this $4,600 card and the first unified shader architecture is just a matter of scale. It's a matter of very, very impressive scale, but it is just a matter of scale in terms of the number of cores that are being supported. Likewise, the major difference between what you have built in lab and what you buy off the shelf is a matter of scale. A significant matter of scale, but still that's just it. And a lot of the architectural issues are best explored by looking at relatively simple versions of the chip. I'll bring up NVIDIA's architectural diagram for their Ampere class hardware. It's kind of incomprehensible, just the number of different cores it has in there. You can't really see that many cores in the diagram. It'll be easier to kind of look at slightly older versions of this just because, the documentation is a little bit better and it's a little bit more to manage all the things happening in the individual diagrams. It is mostly the same. So we'll hop around a little bit. We'll go Tesla, Kepler, and then Ampere and kind of bounce back and forth. Um, Partially, it was where I was able to find decent diagrams and documentation for these things, and others just to get exposure to how things have changed a little bit over time in terms of the naming conventions, if nothing else, but certainly the scale of these devices. It's very similar, and part of the design criteria for the programming languages at runtime as well is that you don't have to necessarily be hyper aware of which GPU you're running on to get decent performance out of it. If you want to get those last few percent of performance, you have to then be hyper aware of what is the capabilities of this particular card, what exact model number is this, or compute capability is this particular card, and then you tweak your algorithm and your implementation accordingly. But in general, from the first unified shader architectures to today, long story short, uh, it's just a matter of scale, and the runtime environment is there to allow you to take advantage of that scale as it is available to you. So our focus is going to be entirely on NVIDIA hardware. I'm not alone in that. It's the way this topic is generally taught, and it's probably the right way to do it. It is arguably proprietary, and it's fine. I mean, we learn you learn lots of proprietary things in your curriculum, so I don't feel especially concerned about that. There are a lot of mediocre CUDA textbooks out there, so watch out if you want to go to the library, you want to buy one. Um, maybe if it's electronic, it's okay that it's not going to waste space on your bookshelf or something like that. For me, nothing beats just playing with examples, and I always feel that way. and downloading the CUDA SDK, which has 70 examples that you can take a look at. For me, the NVIDIA CUDA programming guide is better than any of the textbooks I've found. That guide wasn't always very good, and so there were some early textbooks that became pretty influential in terms of teaching people how to do CUDA programming. But there's probably 60 textbooks now, and I've yet to find one that I feel like I have to have on my bookshelf. So that's a large programming guide. The assumption, in terms of coming from a programming guide as your reference versus a textbook as your reference, is again your juniors, seniors, graduate students. You don't need a textbook anymore to learn how to do a new type of programming. You can figure it out from the source documents themselves. It's pretty well written. Maybe that wasn't always the case, but I would say that guide is actually pretty well written. Have that link, assuming it gets updated as versions update. Have that on your electronic bookshelf. Having said that, so AMD also has the competing approach for doing general purpose or GPU computing. Um, They've kind of started and stopped a few times over the years now, approaching decades at this point. So it's harder to have confidence that this next initiative is going to be one that's worth really dedicating, a chunk of your life to really learning and understanding. Radeon Open Compute is the most current one. 3 years ago, there would have been a different one I would have introduced to you. Um, there's nothing wrong with it. If you look at both, of course, the hardware is perfectly comparable in many ways. It seems like library and language support is feature per feature, at least uh, feature comparison is very similar between the two. There's nothing wrong with using OpenCL versus doing CUDA itself. OpenCL is nice in theory. When it was first introduced, the real advantage of it was the open part of the name. That open source, open specification, tooling and things like that all was supposed to be relatively open to community to mess around with. And so you'll actually still see a lot of academic work that uses OpenCL for that reason. If it's people looking at architectures and languages and compilers, you're more likely to see OpenCL as their framework of choice. If it's actual scientists who are running things on real hardware and just trying to get acceleration, it's almost entirely 99 point something percent CUDA in terms of the academic literature. But those in our discipline who are looking at um, auto generating and accelerators and looking at new compilation approaches and optimizations for getting better performance out of your GPUs, they are to some extent are still using OpenCL for that. The openness nature of it is turned out to be for many of these standards kind of a double-edged sword, right? Same with OpenGL. It's open. That means there's a consortium. That means there's 60 people who get in a room who have to kind of agree on what the next version of it should be. That means it moves very slowly. Whereas NVIDIA could decide we really need this feature in CUDA, and tomorrow they have this feature in CUDA. And so there's some benefit to openness, I guess. It's less proprietary. You're not locked down to one particular vendor. Um, but in practice, you kind of are anyways. So I don't know. So today I still mention OpenCL as something that's also kind of fun for you to look at. Um, Almost certainly start with CUDA first in your own exploration, just from a practical perspective of what works in the majority of hardware you would expect to encounter if you had a task ahead of you to accelerate something. In terms of general market acceptance of the approach and the technology, there doesn't seem to be anything wrong with OpenCL. It's fine. I mean, it's perfectly reasonable. Just like OpenGL is perfectly reasonable, but at least in this instance, it's certainly not a market leader. Not to disappoint any AMD fans in the room, I'm also an AMD fan. So going back to our unified shader view of things. Now, there's a couple things that are a little bit different in this picture than in the previous one. So first off, this is again the unified shader architecture. This is no longer a separate region of the chip dedicated to vertex shading and a separate region of the chip dedicated to fragment processing. It is just these green sea that we see here is the unified shader cores. In terms of what the cores are doing, they're still at this point extremely similar to what we ourselves have implemented for our simple graphic shader processor. We'll talk more about it, but recognizing that the future of GPUs is programmable processing, and the current reality is programmable processing. reorganizing the architecture around the programmable part versus reorganizing it around the fixed function part. It's still there. All of our effectively well established graphics rendering pipeline, you just have to squint a little bit more to see it than in the previous version of the diagram. If we were to trace our execution from vertices to pixels, we can still do it here. Host and input assembler, that's our vertex fetch. In our design, we don't do vertex thread issue. We probably should have, but we just have one thread processor, so one thread issue. We are issuing it, but it's just to one core, doing all of our vertex processing. A lot of it in parallel. That's what these SPs, as we'll talk about, will be handling, which could include, if needed, texture fetch, caching for data, and things like that. Take the results of that processing, and now there's this kind of feedback loop here. Someone ambiguously named thread processor here that is collecting the results of, in this case, to start our computation, the vertex shading that's happening, and we still have that fixed function hardware. Setup, it's now kind of moved into this corner as not being as important. It's still pretty important. Setup rasterization, that's early Z culling, generate our fragment threads. Now these same exact cores that, in fact, some of them could still be doing some vertex processing, they are sitting there waiting for work. They're waiting for their next thread. From our perspective, it's waiting for that go signal, right? Hey, you have new work to do. Read some data, execute these instructions, spit out an output. So now these SPs, these little cores, these shader cores that were sitting here, maybe some of them are currently still doing vertex shading. Others are sitting idle waiting for work. They get work from our fragment thread or our pixel thread issuer here, and then they now do whatever fragment processing is needed, which could include texture fetching. And then at that point, it's not that obvious that this is happening here, but then there's a final connection that says, I'm spitting out fragments, and that would be this connection here. Here's our render output stage here that's doing your MP4 stuff. For the stuff we did get working in MP4, doing your alpha, doing your depth testing and things like that at that point there. So other than all of the cores kind of being put into this collective pool, this is a very similar architecture to the one I previously showed. This is the unified shader. That's the only difference between these two. But in addition to this being the change, which is not, there's now these unified shader cores, there's also now explicit support for GPU computing as well. So it's both. I mean, it's the same architecture, but it's both. It's also just recognizing that while a very common use case of this would be to do rendering, applying our textures, figuring out what our fragment should be, spitting that out to a color buffer. That same exact hardware, now that we have just more general capability to issue threads to these cores, now that we have that ability and we don't have to be, directly connected to the output of a rasterizer to generate fragment threads, for instance, now that we have that, this same exact architecture, and this is not a different chip, this is the same exact chip, just a different view of the same chip, or they'll refer to as computational mode, but it's the same exact architecture, it's the same exact transistors. The only difference is now there's some very basic configuration that says we're not thinking in terms of vertices and fragments anymore. We're now just thinking of input data and threads corresponding to processing that input data. So it is the same exact chip. And I don't know if this picture makes it clear or tries to complicate it a little bit more, that ultimately there's still some way of assembling our threads. So with vertices, we know how that works. We are actually sending vertices to the GPU or telling it to fetch vertices like how we are doing now. And that's what's generating our initial threads. And then the rasterizer is generating the rest of the threads. The only difference in this mode is there's an input thread assembler and a thread execution manager, but it's just handling all of that outside of the context of there being any actual fragments or vertices. This is not a, I mean, it's a significant departure from the computational model, but in terms of data flowing through the system, it's not a radical departure at all. I guess we haven't really talked about what is a thread, right? But a thread is, I'll try to define it without having it be kind of circular here. But a thread is an individual execution of a piece of code. That is all a thread is, right? So while we were previously thinking of threads corresponding to our vertices, and that's fine. It's a piece of data and it's a set of instructions to do some work on that data. Input, instructions, output. That is all that a thread is. So from this perspective, the compute mode of this particular chip, the change is actually a quite straightforward one. Vertices are nothing magical, right? We think of them as being these special things that correspond to um, position data and color data and texture coordinates and things like that. But that's all kind of man-made metadata needed to do our traditional rendering algorithm. What is it all? It's just floating point data of various vectorized types, scalar and vectorized types, and it's a set of instructions we need to be able to process it, and then we do something with the output. Goes to memory or goes to some other location next for another thread to be processing on it next, right? So this change just reflects that fact that threads are threads. We don't have to think of them as corresponding to graphical data, and we can effectively then use the same exact hardware for that purpose. That instead of worrying about, although we still have this view of texture, instead of worrying about texture caches and uniform caches, the kind of things that we're doing to some extent with our SGP design, cache is cache, data is data, right? We need to be able to read and write data from these threads, and so it'd be nice to have caches for them. Likewise, we want to ultimately generate output memory from these individual threads. Instead of worrying about render output units, you can just have sort of general load store units. It's the same hardware. So the valid question Nathan asked is, where did the rasterization logic go? Physically, and we talked about this a few times, and I never gave you a definitive answer because I don't know the definitive answer. Do we still have fixed function rasterization hardware on modern GPUs? I believe the answer is yes. Good luck finding a definitive answer to that, and if you find it, let me know. As I meant, we've talked about this before. It is still there. It would just be effectively, think about how this would work in practice, replaced with some pass-through logic instead for this compute mode. Think of it just a single bit in your configuration register space for the design, where you would have to tell the chip that, by the way, the current task is OpenGL, it's doing rendering. That bit is high. We turn that bit low, or we turn on another bit. We're now in compute mode. All this hardware is still there. Those arrows are likely still there. I mean, right? Those arrows correspond to muxes and wires, like anything else we do, right? But we're just setting this mode. We're saying, by the way, the output of our threads doesn't need to correspond to anything that gets interpolated. We're not corresponding to triangles for this general computational mode of things. So whether it just completely circumvents it, or whether it turns into some pass-through mode for, it's hard for me to say exactly what's happening there. Same with the render output, right? There's still all that logic that you built to check depth, to do alpha blending and all that kind of stuff. It doesn't go away. I mean, the transistors are still there for it, but we can presumably, although it doesn't say necessarily in any of the documentation, we can presumably use the same exact hardware that's there and have it then be configured as a general load store unit versus something that's doing a depth comparison and an alpha blending and all that kind of things, right? Because it's the same operations. And even if it were a state machine versus a programmable piece of hardware, you could still have a configuration for that state machine that would effectively be a allow all, right? Which we have already. Allow all data that we want to write to memory actually be written to memory, or always read first and then write to the value that we have in memory there. So long story short with regards to that, these are two views of the same exact piece of hardware. And maybe you could have drawn this version in which for compute mode, it's literally the same boxes, but just some of them are have muxes in front of them, or just have a pass through instead, or have some mode in which they're not doing any of the graphics things we've been building on all semester here. But that's the big innovation, though. Again, going back from the view of computing that we have to trick everything into being a computational application, to being a graphical application to be able to do some computation, to then recognizing that because there's some value in having unified architecture in the first place, vertex shading is not all that different than fragment shading. It's just a matter of workload balance more than anything else. If we have this, then directly kind of natively supporting computation on our GPU, if not for free, is had for a very, very low nominal overhead cost in terms of architecting the system. Turning things off is usually easier than adding new features, and that's all this is ultimately reflecting. This thread issue, which again, this is a logical box. What does this mean in terms of actual architecture? It's hard to say. There's some piece of hardware that's dedicated to managing all the threads in the system and kicking them off. It's a bunch of FIFOs. There's no doubt about that. So our design philosophy is not wrong from that perspective. But if anything, switching from graphics mode to compute mode from a thread management perspective is just presumably a slightly different state machine or a slightly different algorithm associated with this. We're no longer tracking vertex threads and fragment threads. Everything is just a compute thread. And so the relationship, if anything, is simpler here than what it is here. There's less things to keep track of here. So we're removing things or we're circumventing things. So it's kind of sort of for free, or at least for a fairly nominal cost in supporting this compute mode. Users can now take advantage of all these nice little green boxes. And when we look at modern hardware, I think it's fair what I mentioned before. The main difference is just that of scale. Certainly with the resolution as we transmit over Zoom here, you probably can't see much at all with regards to this. It's just a lot more little green boxes. That is the major and primary difference. There are other differences, but that is the primary difference between 2021 NVIDIA hardware and 2006 NVIDIA hardware. But the nice thing is that in allowing for those unified shader architectures, it's a win essentially for everyone involved. NVIDIA still gets to keep building hardware that does this very well. That does graphics rendering as efficiently as possible, allows for more realistic real-time effects, all the kind of things that we kind of sort of half covered this semester. And in doing so, as long as there's sufficient hooks to kind of circumvent some of the things that are required fixed function hardware for doing graphics, in supporting that, they are effectively getting, with I think relatively little design overhead. It's easy for me to say, but with relatively little design overhead, they're getting this as well. And if you had wanted to support it, no one suggested this for a project, but if you had wanted to support just GPU compute with your SGP, I think we could also do that as well. We would just need to have a better model for fetching vertices than what we do now. Um, I think it's mostly driver than anything else. And you would just re-architect the system so that it wouldn't have that rasterizer core in there in general, so we could use those chip resources for having more shader cores. So as they continue to innovate on the graphics side and just follow kind of technologies of scale with regards to transistor density and things like that, then we can get to this. And they can charge us $4,500 for a single device, and we feel like we're getting a relative bargain in the world. But this is why this is important. So this scale of this picture is a pretty important thing. It's the transistor budget associated with something like this. It's the percentage of that transistor budget that's dedicated to computation. I didn't define computational density, but it's essentially that. What percentage of our real estate is dedicated to computation versus all the other cruft we need to be able to support general purpose computation. Our control logic, our scoreboarding, our data dependency detection, all of the cache and related things. And by and large, GPUs have been able to dedicate more of their real estate budget to computation versus all the other architecture stuff. And so these chips are still pretty exciting from that perspective of, for a particular form factor, for a given power budget and price budget, how much computation can I wring out of my workstation? And at least as of today, outside of some very specific dedicated hardware and dedicated applications, these are still these are extremely competitive. These are still the best bang for your buck for doing that. So even though architecturally from this picture, although it looked quite a bit different, it's really just the green squares are just smaller. And instead of having 256 of them, we have over 10,000 of them, which makes it harder to kind of see them in the picture. Outside of that, and everything else scaling accordingly. A little bit of clock frequency scaling, the amount of cache scaling, things like that. And outside of some slightly new dedicated hardware to do certain applications a little bit more effectively, it's really just more of the same. It's a it's an outstanding performance in terms of technology scaling. Architecturally, we're on pretty good footing, kind of understanding this architecture and recognizing that if you can afford it, this one's going to give you more parallelism, more cores, more threads that you can execute in a reasonably effective way. Any questions about that before we start to jump into the programming side of things for this? Report in the chat if any of you have an Ampere class hardware. I want you to run some benchmarks for me. So there's a couple different now we're talking NVIDIA hardware, so we're talking NVIDIA programming interfaces. There's two different classes of interface. So there's still sort of an assembly level interface. This is what NVIDIA refers to as their parallel thread execution or PTX assembly. We have to be a little bit careful with the term assembly here. So it's not assembly as you would think of it in the CPRE 381 sense of the word. It is and it isn't. um, in that it is an assembly language format. We can take a look at what it looks like in practice here in just a moment. It is an assembly level format, but it's still actually a layer removed from the underlying machine code that runs on the hardware. So I mentioned it briefly in the Discord yesterday. This concept of sort of a hardware abstraction layer, which is a way of abstracting out sort of the interface between the assembly and the underlying machine code running on that device. It's a very useful thing from a portability perspective that if I target that intermediate layer, it can be a very low level assembly layer. You can do the kind of optimizations you would need to do, but there's still yet another layer of translation that happens. People talk about the openness of NVIDIA hardware and to what extent it's possible to write open source drivers for it. And this is fundamental part of the issue that there is this target that everyone can hit in an open way, this PTX target. There's an extra layer of translation that happens. So when you see the term sort of virtual assembly or virtual machine execution of it, it's not referring to large VMware type of things that are happening. It's referring to the fact that there's this additional layer of translation that's happening from assembly format to even lower level assembly format, from something that's generalized across all classes of NVIDIA hardware to something that's specific to that particular device that you're currently running on. And it tends to happen just in time as well. So these binary blobs get loaded relating to the PTX, and then as they get loaded, they get translated to this not open, not well published, not well explored format that is proprietary to NVIDIA and subject to change at a moment's notice from one GPU to the next one that gets released. So we'll look at PTX. It's not generally an effective way to do programming because assembly is not generally an effective way to do programming. It'll be fun, at least to some extent, to explore what makes it different from the assembly that we've already done. Um, this semester's 480 is a little different than previous ones in that we did develop our own unified assembly format that is, while not inspired by this necessarily, you should be able to look at it and see some of the similarities. It's doing the same kind of math, so it's going to look fairly similar in terms of what is supported in the assembly and the ISAs for our architecture versus NVIDIA's virtual target there. And then there's finally the CUDA extensions and so-called high-level programming languages. In the early days, CUDA was just C programming. That has changed. I don't use most modern C++ features. They intimidate me a little bit. They make code incredibly difficult to read and debug, but that's just might be my old school ways. But it does support modern C++. And there's either extensions to programming languages or existing library support for essentially everything else now as well. So when someone says this code is done in CUDA, well, CUDA at least originally stood for just Compute Unified Device Architecture. So anything that targets GPU compute on NVIDIA devices is CUDA code there. Historically, it's referred to C and then later C++ extensions that allow you to have relatively um, low level control over how your code is being partitioned and executed on a particular GPU device. The Python bindings for CUDA are extremely nice. They're basically the same. They give you a very similar amount of low level control. Um, MATLAB is more of a library-driven approach, so it's like analyzing your code and trying to map it effectively to the underlying hardware. Uh, it depends on what your goals are, certainly. Oftentimes, I mean, it certainly depends on it. I'll say it again. It depends on what your goals are as a programmer, right? If your goal is to take advantage of GPU hardware as it generally exists in the wild, you're better off just mapping your code to existing libraries. Let the library developers worry about how they're going to best optimize for an underlying AMD versus GPU hardware. If you have a individual particular application and you have a particular hardware target, let's say you're working on in the high performance computing world and you know here's this supercomputer that has these NVIDIA nodes on them that you're wanting to target your code towards, then you really want to dive into CUDA. Then you really want to look at, okay, how do I lay out my thread so that I get the most out of this particular class of hardware that I know my code is going to run on, and it's going to run on very similar code like that. It's not meant to run on everybody's hardware that exists in the world. So that distinction between library developer versus application developer is always the case, and the style of code you would choose to write, the level of detail in terms of or level of abstraction of the code that you choose to develop in, um, you always have to make that design decision. Um, as I've gotten older, I feel like portability and readability has become more and more important to me than squeezing out the last particular percentage of performance. But it depends. And in your entry level position, that may not be your call to make. Learning CUDA itself will still be very helpful for understanding parallel computing in general. As a good use case, a relatively easy entry point for doing parallel computing. The things that CUDA has by and large supplanted um, were a lot harder to use and a lot more annoying to work with. So in big HPC environments, you're doing a little bit of everything. So you'll have MPI code that it's communicating between individual nodes that maybe have OpenMP on the CPU side and CUDA on the GPU side. And so you're managing all those different frameworks. Um, but of those, CUDA is a really straightforward way to start. Squeezing out the last few bits of performance is is a academic endeavor like anything else. It involves understanding, profiling, really reading all the documentation. Like in anything else, that's the case. To get reasonably good performance, I have my 10,000 shader cores on. Having won the lottery, I bought one of these, and I have my 10,000 shader cores. If I want to get reasonably good performance out of it, CUDA gets you started very quickly. So for that reason, I actually do like it. It's a very fun way to get started with GPU programming. And whether we do PTX as our interface, and we won't in terms of developing anything from scratch, or you're using CUDA, whether it be C, C++ bindings, or using some other language framework, the key concept is exactly the same. So the idea is that all of our threads, a lot of these claims need a small asterisk next to them. But for now, all of these threads are executing a single kernel in parallel. So these are terms that existed well before CUDA came around, but oftentimes now we use them solely in the context of CUDA. Our kernel, which is a CUDA term, but it exists before, is our block of code that we're wanting to execute in parallel. And we're going to have all of these threads that are executing that single kernel in parallel. Maybe not entirely parallel. There could still be some serialization happening there, but in theory, at least, there's all of our threads that are taking this block of code and they're mapping it to that sea of green shader cores that we have from the previous diagram. To get full utilization on one of those cores, certainly it gets harder as the cores get larger than easier. You'll need thousands and even tens of the hundreds of thousands of threads required to get full utilization of it. If you have those many cores, to actually take advantage of that chip, you need that many more threads. As we'll see, the fundamental trade off in designing for a CUDA based NVIDIA piece of GPU hardware is keeping it busy. How do I give it enough meaningful work to do such that when one of those threads out of the thousands have to sit idle, and every time you miss in the cache, nothing has changed there, you're going to sit idle for a few hundred cycles. Can I give it enough work to do that every time that happens, every time one thread has to sit idle, there's another one ready to take its place? And that's the other part of this key concept here, that context switching between threads, intentionally via the design of CUDA and the underlying architecture, is, if not free, is essentially free. In my traditional CPU, I want to do context switching. There's some serious work I have to do. I have to store the state, and everyone is at least in 308 now if you haven't already taken it, I think, for the most part, right? If you if you want to switch one thread and replace it with another thread, I have to, in some way, shape, or form, keep track of the state of the thread I'm getting rid of. I have to store it somewhere. It's a copy operation. And it's a low level copy operation because it's not just a block of memory I'm copying, although that could be part of it. It's also all of the register related runtime associated with that particular thread. It's expensive relative to the frequency in which one wants to switch between threads on a traditional CPU. On a GPU, um, not coincidentally, through intentional design, architectural trade offs made, that context switching between threads is essentially free. And you may already, I think, hopefully already be asking, well, how can you possibly do that? I have a set of registers. I go from thread A to thread B. How do I avoid overriding those registers such that the code is still correct and it's still executing properly? Part of this has to do with, again, the genesis of these devices, right? The initial use case for these unified shaders and where they came from in the first place was to do graphics processing. There was very little state associated with each vertex when I'm doing graphics processing. Vertex comes in, I have a kernel I execute it for, my shader code, I spit it out, I'm done. Same with fragments. The code that I'm running for rendering is one or two or three or so, a very small handful of kernels. There's a kernel for processing my vertices, a kernel for processing my fragments, maybe for geometry and other things as well. We have a separate kernel associated with that. That explains why we have this concept in our CUDA as well. Thousands of threads required for full utilization. Well, part of that is just kind of a natural byproduct of the fact that if we're going to have hundreds of cores and occasionally those threads are going to need to sit idle, we'll need more than hundreds of threads. And the actual number varies wildly based on the application, but it's a pretty significant multiplier of the number of cores. If I have 256 cores, I'm going to need thousands of threads to keep them happy because when we miss in the cache, that penalty, there's no magical way to avoid it. That penalty still exists of waiting for DRAM, waiting for that latency of DRAM, a few hundred cycles of stalling. We don't want to stall for that period of time. But again, going back to the original graphics context, we also kind of got that, right? Getting 1,000 or millions of threads is something that just naturally happens when we do graphics processing. We're rendering triangles, there's enough of them, and they have enough fragments associated with them. And while we're limiting ourselves to, one fragment per location in our screen for a lot of our applications, it could be many, many, many such fragments per location in our screen, in our color and depth buffers. Generating millions of threads is something that's hard to avoid even, but it's a very easy thing to do in the graphics context. The hardware is built to handle that many, thousands and millions of threads. And then finally, for free context switching, we'll see what that means from the architectural perspective of what these cores are capable of doing. So this is more straight from the CUDA guide, more marketing than anything else. So scalability is the design goal specifically for that reason. Can I support my $100 GPU and my $4,000 GPU with roughly the same piece of code? As I already briefly mentioned, in theory that is the case. In practice, you leave a lot of performance on the table if you write code that's completely general to that case. And most fairly advanced CUDA codes that you will find in either in the SDK or just example applications that have been published for taking advantage of NVIDIA hardware. There's a lot of bookkeeping code in there to query and say, what GPU am I actually running on? Consequently, let me change my thread and data layout accordingly. And also another design goal of CUDA was to allow for so-called heterogeneous processing. Not really as a first-class design consideration, but kind of as a happy side effect of how these codes get launched on the GPU. We already have that in our existing GPU as well, right? The CPU is responsible for managing the execution of all this graphics rendering or compute threads that we may have. And unless we tell it to, it can just keep going. I've launched all my vertices, I've copied them over, I've done the draw call. We explicitly in the driver ourselves had to add those wait statements, right? Had to add those blocking codes that would tell the CPU to stop until the GPU is ready. Now, in the compute mode of things, we may still want that. We may still want to explicitly synchronize, and CUDA allows explicitly to wait for GPU to be done before CPU continues. And that's a very common use case. But sort of for free or kind of by default, we don't have to do that. So one can imagine a scenario in which you're partitioning your code such that the GPU is taking some load of the computation and the CPU is taking some other load of the computation. And CUDA does allow that kind of natively in the infrastructure for launching these kernels on the GPU. Um, I don't see too many examples where that's very cleverly done. I think it's a very challenging thing still to do from in an intelligent fashion to partition it in a meaningful way that you can guarantee that either they're allowed to completely run freely of each other, which is not a common thing I see, or that you can kind of balance it such that when one is done, the GPU is done, the CPU is also likely to be done at roughly the same time. Because if one is waiting for the other, it defeats the purpose of having it run in a heterogeneous mode. That's a very tricky thing to do, but at least the hooks are there. It's something you're capable of doing. Oftentimes, and if you look at the SDK for it, CUDA SDK, the CPU is there just to say GPU go, collect results. GPU go again, collect results. And that's still, because of the density of our computational resources on the GPU, that can still lead to pretty significant speed ups, even if the CPU is just there to kind of manage the whole process and not do any actual computation itself. Talk a little bit about the terminology one final time before we start to bring up some code examples here. So our parallel programs, those are the kernels on the GPU. The term kernel, you may be thinking like operating system kernel. Small self-contained piece of code is what a kernel is, right? Um, that term pre-exists GPUs by decades, but that's the term that's used in the CUDA documentation. So I'm executing the kernel on the GPU, the block of code. You can think of it like a function, but they also support functions. So it's an individualized block of code that's running on the GPU. And then in the terminology, you'll see the GPU refers to as the device. With a little asterisk there, I mentioned only one kernel executing at a time. At least that's a good simplifying assumption for us going forward, that we're executing one kernel at a given time. And then we're executing that kernel across our hundreds to thousands to millions of CUDA, thousands to hundreds of thousands of CUDA threads here. They're all running the same code. So when we write these kernels, that's going to be a little different than our traditional programming model of computation, even if syntactically it looks like C, C++, or our Python here. Syntactically, it's the same. It's like we're writing a function, but that function has to operate with very little state. That function has to operate such that I can launch 10,000 threads, all running that same compiled bit of C or C++ code, but they would execute in such a way that there was some reason to do that. That they're doing things that have some parallelism associated with it. I don't know if I've explained that well, but that is the important part, which is why a good chunk of each kernel is also this kind of bookkeeping code of, okay, I've entered my kernel, I'm a thread, I should know very little to nothing about my other threads in the system. I don't know if they've launched yet, I don't know if they've finished yet. I need to figure out what work is mine to do next. From graphics rendering perspective, that's kind of something we get for free. Yeah, we have to kind of keep our vertices together to make sure we rasterize them. We assemble them into triangles ultimately. But once we get to fragments, for the most part, fragment has very little knowledge of what every other fragment is doing. And if we do our depth buffering and blending correctly, it doesn't matter which order we render our fragments. So that's an easy thing from that perspective. Fragment just gets an ID, it knows which fragment it is, it does its fragment shading task. Now, from the general purpose computation perspective here, we have to be cognizant of that fact that we're not doing fragments, we're doing just input, processing, output, and all of my threads are going to be running that same block of code. So that block of code is going to have a lot of bookkeeping to just keep track of who am I, where am I, what do I need to do, so that I can operate completely independently of all the other threads here. And I think a pretty common question is, well, my code is inherently sequential. I have to do X, then I have to do Y, then I have to do Z. That could very well be the case. A lot of things we have to do are inherently sequential. It's not going to map very well to your GPU, right? So the GPUs aren't going to be magic from that perspective. we have all these shader cores or these CUDA cores, whatever you want to call them, available on the chip, tens of thousands of them now. We have a programming framework that allows you to very easily launch 10,000 threads without really thinking about it. But if your application doesn't have that level of parallelism, rendering does, right? There's enough fragments to keep any GPU busy. General purpose computation, if yours is something that's inherently sequential, I really can't go to the next part until I've completely finished this first part, depending on what you define by those parts. And I'm only really operating on one byte of data at a time. I can't really go to the next byte until the previous byte is done. So be it. There's all sorts of compression schemes that work out that way. Certain crypto that you really can't go to the next part until the previous part is done. It's inherently dependent and sequential. So be it. GPU is not the right target for you. You will get very nominal gains, or your mode of execution has to be fundamentally different in terms of how you do that parallelism. Maybe individual compression task is inherently sequential, but perhaps you have a situation in which you need to do 10,000 compression tasks for 10,000 pieces of data separately. Then maybe you get some advantage there, but it's not magical in terms of getting parallelism out where your application or your algorithm doesn't inherently have parallelism in. So we talk about architecture and programming environment leading to different models of computation. How we think about how the computation has to be done, right? That's what our model of computation is. When I tell you you have to implement a state machine, well then the next thing you think of is, well, let me think about the different discrete states of the system and how they connect to each other. What arrows or what edges do I need between them? When I tell you you have a sequential programming model, okay, what for loops do I do? How do I think about task to task to task to task sequentially? Now, you can think of CUDA and you can think of GPU computing as both architecture and language frameworks, but it's also a corresponding model of computation. If you're being told, sometimes it's a little backwards, but if you're being told that your task is being mapped to a GPU, then that should also influence how you think about the task, which is I'm going to have relatively simple kernels that need to be able to operate completely independently from each other. And not just six or not just 25, thousands to tens of thousands of those threads executing roughly in parallel to each other. And not all tasks will map to that. A large number of them do. It's not a coincidence the kind of examples you tend to see that things that are highly parallel, sometimes referred to sort of embarrassingly parallel as well, in which there's a lot of work to be done, but not a lot of dependencies between the work associated with them. So a big chunk of your CUDA code, after you're already thinking in terms of that model of computation, has to do with that thread management task, which is I have all these thousands of threads. There's going to be some index or IDs associated with each of those individual threads at runtime. My code now needs to do that management of which thread am I, which data location and memory should I actually be reading from to do my computation to spit my result back out. And finally, where I'll leave things for today, and I'll show you this very simple, trivial example here. This is our first CUDA kernel here. Syntactically, it should look very C, C++y. That has changed a little bit over time, but the idea, at least the design consideration, was this was meant for originally C programmers to not have to learn something fundamentally different to be able to get GPU performance back out. So that global keyword is required for our kernel functions. Typically, the inputs to your kernel, and again, it's not exactly a function call. It is a kernel call, and so there's going to be thousands of threads that are going to be launched, and they're all going to have the same inputs. So typically, because they're all going to have the same inputs, we're generally passing pointers as inputs to our kernel. All of the threads, the tens of thousands of them, are going to be aware of a base location in memory. And then the other thing is some sort of offset addressing per thread based on some assigned thread index. So this doesn't show, how this gets assigned. That would be your thread manager that's handling that determines, and we will talk about this on Thursday. I've organized my threads in a certain way. It's not just as simple as saying I want 10,000. You have to determine a multi-dimensional organization of threads before you execute them. And then accordingly, various indices get assigned. You can think of them as IDs or indices. It's either way is fine. Get assigned to them in that multi-dimensional space. And consequently, one way, and this would be a one-dimensional layout of threads with how it's written here, one way you get that parallelism back out, and one way you allow for all these threads to be independent of each other, is to first specify our base addresses, input pointer, can't see my hands, input pointer, output pointer there. We then use those thread indices, which our thread manager is going to assign to each thread, to say, okay, we all have the same pointer. What value am I responsible for this particular thread? And that would be one way to do it linearly. Each thread gets a different location in memory. Doesn't have to be all different locations, but there has to be parallelism involved for this to be meaningful. We do some sort of function, and that can be a function call. That can be short, can be a large function. Some functions will map better to CUDA and underlying GPUs than others, but it's doing some math, doing some processing there, separate from the rest of what's happening here. And then likewise, our output is getting stored in memory based on the offset to the base pointer that is also based on the same exact thread index that we have here. That's one way to do it. This would be a piece of code for which in parallel, we're allowed to operate on every value of an array and store the value of the array independently. Most applications aren't so clean and easy as that, but this is what all kernels are going to have. A little bit of a signifier to indicate that this isn't just a regular old C function that the NVIDIA compiler should compile this versus the GCC or whatever version compiler. Usually pointers is the second characteristic we would see here. That's just one way to manage that parallelism with the data parallelism approach. There are other approaches, but that's a pretty straightforward way. And then an increasingly noxious amount of kind of thread management in our logic. This one's pretty straightforward. Just visualize an array of data. Each thread gets one. They don't need to know anything about what the other threads are doing. That can get a little complicated, but that's the other third feature that you would have here. That's for our particular kernels. A little bit more in CUDA that we'll start on starting on Thursday about how we manage that whole process, how we keep track of all the computation that's happening. And throughout we'll be talking about the architecture associated with that. Let's leave things here for today. I'm glad we're finally getting to this topic. It's kind of a fun thing to play around with and explore. Looking forward to seeing everyone in lab on Wednesday, and otherwise, enjoy your projects.